Hello guys, welcome on Tesla Adventures. In this video, we are going to start the concept illustration problems which are based on the expansion or compression of air column bounded by a liquid. This is a special type of problems which we are calling as type 2 problems, and you would be getting this problem in JEE Advanced paper mostly. Yeah. Now, in this first question, you can see that there is a tube, a glass tube, in which there is air, some amount of air, which is at 300 Kelvin, and this air is being trapped between this closed end of the tube and this mercury column. The length of this mercury column is 19 centimeter, and we have to find out the length of the air column when this tube will be inverted. First of all, let us see that the most important thing which I wish to point out is the fact that when this, you can imagine that when this tube will be inverted, then mercury will be on the upper side of the tube, like that, and air will be trapped. And this inverted tube will have mercury. This is mercury, and the remaining part is air below the mercury. So you can see obviously that this air would be compressed, and you always have to consider this process as isothermal process, which means that you should always consider that temperature remains constant in such type of inversions. And now it is in this question, it is particularly mentioned that this process is isothermal process. So we have to find out the length of this air column. So there are requirements of two equations, which is the equation of pressure by fluid dynamics and the equation of isothermal process. So let us see that how we will make those equations. So let us suppose that initially the pressure of air was P1. So we know that at this point pressure is P0. So we can say that P0 will be equal to P1 plus H rho g. This is 19 rho of Hg into g. Okay, we know that the pressure at this point will be the sum of pressure of air as well as pressure of mercury. So P0 is obviously we know is 76 rho g. Rho is the mercury density, and P1 plus 19 rho g. So you can see that P1 will be equal to 57 rho g. This is P1. Okay, and now when we have inverted the tube, then let us suppose that pressure of the air column is P2 and pressure above the mercury is obviously P0. So we can say that P0 plus H rho g, this is H rho g, and obviously the length of mercury column will remain same because it is solid. So P0 plus this is 19 rho g will be equal to the new pressure P2. So P2 will be equal to 76 plus 19 rho g. So we can say that P2 will be equal to 95 rho g. Now you can see that this air column is being compressed by mercury. So this compression is isothermal process. So we will use the characteristic equation of isothermal process, which is P1 V1 and it is equal to P2 V2. And you should always remember that P1 V1 is the initial pressure and initial volume of this column, and P2 V2 is the final pressure and final volume of this column. So the initial pressure was 57 rho g and volume was 30 into area. Now let us suppose that whatsoever be the area of cross section of the tube, let us use that area as A. So the volume will be 30A, and that would be equal to 95 rho g into new volume will be X into A. So you can see that rho g and A will be cancelled out, and x will be equal to 57 into 30 by 95. So x will be equal to 18 centimeters. This will be 18 centimeters. Okay, and in the second part is the fact that to what temperature we should heat the air column again so that it regains the original volume. So you should always remember, and you should always note the fact that when we will again heat this air column, then obviously this mercury will slowly rise up and this air column will slowly expand. And in this complete process of expansion, when the mercury will be rising up, the pressure above the mercury will be the atmospheric pressure, which is constant, and the length of mercury column is also constant. So the pressure at below point of the mercury will be constant, and therefore the pressure of gas will be constant. So this will be a isobaric expansion. So in isobaric expansion, we can say that V1 by T1 will be equal to V2 by T2, and again volume finally will be 30A, because the gas has attained the new initial volume again. So 30A divided by the initial temperature. Now when we inverted this tube, the temperature was 300 Kelvin, and we assumed that this process is isothermal. So we can say that at this instant of time, temperature is again 300 Kelvin, and in fact initial volume is x into 18, which is in this case x is 18 in fact. Yeah, so initial volume is 18 into area divided by the initial temperature is 300 Kelvin. And finally, when the air column attained this length 30 centimeter, then the volume becomes 30A, and the new temperature, we have to find out the new temperature. So T2 will be equal to 9000 upon 18. So T2 will be equal to 500 Kelvin. And if we wish to find out the heat supplied in this process, then obviously we can use NCP delta T, because this is an isobaric process, so heat supplied would be NCP delta T. Now let's move on the next question. In this question, you can see that there is a rectangular narrow U tube which has equal arm length. Length of each arm is L, and the base length is also L. Now this tube is filled with mercury as shown in the figure, and this end of the tube is sealed and it is heated by a torch, and due to that heat this air expands and it pushes the mercury out of the tube completely. So we are completely pushing this mercury out of the tube. If the density of the mercury is rho and the cross-sectional area is S, and we have to neglect the thermal expansion of mercury, so we have to find out the work done against gravity as well as the work done against atmospheric pressure. So let us first of all draw the situation. Now you can see, let us draw the situation. This is, you can see that this is the U tube and this end is sealed, and obviously at some instant of time this would be the situation. You can see that if we have pushed this mercury completely in this arm, then obviously this length will be L and this length will be L. The pressure at this point A, PA, will be P0 plus L rho G, and this pressure will be equal to the pressure at point B, and the pressure at point B will be pressure of gas. Okay, so you can see that this situation, initially the gas pressure was P0, because these two levels are same, and therefore the pressure at these two levels will be same. So we can say that obviously pressure is changing, and the pressure initially was P naught, and now the pressure of the gas is P naught plus L rho g. So pressure is changing. So this is not a isobaric process. Obviously this is not a isochoric process, and it is also evident if you can find out the pressure into volume at any instant of time, then you would see that P into V will be different at different instants of time, which means that it is neither isothermal process. So if in such kind of process we need to find out the work done, we do not try to use thermodynamics laws. In fact, we use the situation that the gas is doing the work against the two forces which are restricting the gas. The one force is atmospheric pressure, which is pushing this mercury in the downward direction from this point, and the other is gravity, which is not allowing this mercury to go up. So gas will be doing work done against these two forces. So if we can find out the work done against these two forces, and if we can sum up those work done, then that total work done would be the work done by the gas. So first of all, let us take this problem step by step, and let us first of all find out the work done by gas against atmospheric pressure. So to find out the work done by gas against atmospheric pressure, let us neglect gravity. Neglecting gravity. So if we neglect gravity, then we can say that pressure of the gas at all the instants will be equal to P naught. Pg will be equal to P naught at all the instants. Okay, so obviously the initial volume of the gas was S into L by 2, this volume, and when we will completely expel the liquid out of the tube, then this complete tube will be occupied with the gas. So the final volume will be equal to the complete volume of the tube, which will be 2L. In fact, this will be L, L and L. This would be 3L into S, which is cross section area, and this will be the final volume. So the work done will be equal to P delta V, because P is constant if we are neglecting the gravity, and P is equal to P naught. So it would be P naught delta V, and delta V will be equal to 3 minus 1 by 2 into SL. So it would be equal to 5 by 2 P naught rho, this is SL. So work done finally will be equal to 5 by 2 P naught SL. This will be the work done. So A is the correct option. Now let us see the work done against gravity. Now let us use the next page. Let us see that if we draw the initial diagram, and we know that work done against gravity is obviously delta U, change in potential energy. So initially this was the liquid, and U initially was equal to M. Now let us consider that total mass of the liquid is M. So this would be M by 4, this would be M by 4, and this would be M by 2. So total mass would be M, and the initial potential energy will be twice of M by 4 G, and the center of mass of each of this liquid will be at a height of L by 4. So initial potential energy will be mg L by 8. Now when we will expel this complete liquid out of the tube, then obviously we can see that we would be pushing this liquid. Now let us suppose that there is dm small masses present in the liquid, and if we integrate all the dm, then it would make m. So if I concentrate on this last mass, dm, and if I say that if each of the mass dm has finally reached this end and the last mass has finally reached this m, then obviously the complete liquid will come out of the tube. So what I am saying that I am pushing each of the dm to this point. So the final energy of each dm will be at this position, and it would be dm into g into L. So U final will be equal to integration of dm into g into L, and g into L is constant, so integration of dm will be m. So U final will be equal to mgl, and obviously delta U will be equal to 7 by 8 mgl, and this is 7 by 8, and m will be the mass, and it would be equal to density into volume, and volume is area of cross section into total length of liquid in tube, which is 2L. So this is 2 into rho into S into L into G into L. So it is 7 by 4 rho S G L square. So work done against gravity is 7 by 4 rho S G L square, and work done against the atmospheric pressure is 5L by 2 P naught S. Now we move on the next question. In this question, you can see that there is a beaker containing mercury, and an inverted closed glass tube is being dipped into the beaker, and this glass tube is above the mercury level by a height of h0, and there is some gas which is being trapped inside this glass tube on the top. Now it is also given that atmospheric pressure is equal to h0 rho g. It is given in the question that P0 is equal to h0 rho g, and we have to increase the temperature of this gas by a amount of delta T. So we have to find out the amount of heat supplied to the gas. Now let us see the situation. So when we will supply some heat to this gas, it will expand and it will push down this mercury in the bottom side, and therefore we can say that if this gas will expand and it will push down the mercury, the pressure of gas will change, because this level, because at any moment of time, let us suppose that this is x, or let us suppose that this is x, the part of the tube which contains the gas is x, and let us suppose that area of cross section is a, and this height will be h0 minus x. So at this point pressure of gas is P. So we can say that P plus h0 minus x rho g is the pressure at this point, and this will be equal to P0. And P plus h0 rho g minus x rho g is equal to P0, and P0 will be equal to h0 rho g. So P will be equal to x rho g at any moment of time. Okay, and we know that delta U will be equal to n CV delta T. Okay, so delta U will be equal to n is 1, CV is 3 by 2 R, and delta T is the temperature given. Now if we have to find out dQ, so we can find out the dQ by delta U plus dW. Now we have to find out dW. So let us suppose that at any moment of time this level goes down by a distance of dx. So the work done by the gas will be equal to integration of P dV. So work done will be integration of P, which is x rho g, and dV will be equal to area into dx. Okay, so this is the first equation, and we can see that this work done will be equal to x square by 2 rho ga, x square by 2 rho ga, and the limit of x will be x initial or x1 to x2. Okay, now let us do another analysis. Let us see that the T initial temperature was P1 V1 upon R, because number of moles are 1. So initial temperature, or we can see that we can say that this is T1 and it is P1 V1 upon R, and T1 will be equal to P1, which was the initial pressure of the gas. So it was x1 rho g into initial volume was x1 into area, and this is R. So T1 is equal to x1 square rho g A by R, and T2 will be P2 V2 by R. So T2 will be equal to x2 rho g into volume will be x2A by R. So T2 will be equal to x2 square rho g A by R. And we know that T2 minus T1 is given as delta T, and it would be equal to x2 square minus x1 square rho g A by R. And if we substitute this x1 x2 in this equation, we can see that it would be x2 square minus x1 square by 2g rho A. So rho g A into x2 square minus x1 square will be equal to R delta T, and therefore in this equation we can substitute this value, and the work done will be equal to R delta T by 2. So the heat supplied will be equal to delta U plus dW. So heat supplied will be equal to 3 by 2 R delta T plus R delta T by 2. So it would be 2 R delta T. So this is the final answer, that heat supplied to the gas for this purpose is 2R delta T. Now we move on the next question. In this question you can see that there is an ideal gas which is filled in this chamber, and the initial pressure, volume and temperature of this gas was P0, V0 and T0 respectively, and there is a U tube that contains mercury, and it is seen that when an extra amount of mercury, which is 20 centimeter of mercury, is poured in this limb of the tube, then the temperature of this gas gets doubled, and the final level of the liquid in this limb is remaining the same. Still it remains the same as the initial level, and the surroundings is vacuum. So we have to find out the initial pressure of the gas in this case. So we know that if, let's suppose, initially this height was x1 and this was x2, and here pressure is 0 because vacuum is present at this end, and in this case the initial pressure is P0. So pressure at this point will be P0 plus x1 rho g, and pressure at this point will be equal to x2 rho g. So we can say that P0 will be equal to x2 minus x1 rho g. This is P0. And finally, when we have poured extra amount of mercury in this side, then that is 20 centimeter, then obviously the pressure of gas will change to keep the volume fixed. So P will be P, and P plus x1 rho g, because this x1 will remain constant, will be equal to 20 plus x2 rho g, and P will be equal to 20 rho g plus x2 minus x1 rho g. So P will be equal to 20 rho g plus x2 minus x1 rho g is P0. So this is P, and it is also given in the question that temperature of the gas is doubled. So if volume is constant, we can say that P1 by T1 is equal to P2 by T2. So P1 was P naught and T1 was T naught, and now P2 is P and T2 is 2 T naught. So P is equal to 2 P naught, and therefore P will be equal to this one. So this is 20 plus 20 rho g plus P naught will be equal to 2 P naught. So P naught will be equal to 20 rho g. So which means that the initial pressure of the gas was 20 centimeter of mercury column. Now we move on the next question. In this question you can see that there is a glass tube which is closed from both the ends, and it has equal amount of air on both the sides of mercury, and the length of the air column initially was 40 centimeter on both the sides. The mercury column is of length of 20 centimeters and the total length of the glass tube is 100 centimeters. The initial temperature of air was 27 degrees Celsius on both the sides, and at some time we have changed the temperature of the air on both the sides, and one side is maintained at a temperature of 0 degrees Celsius and the other side is maintained at the temperature of 127 degrees Celsius. So we have to find out the final lengths of both the sides of the air columns. Now we can assess the situation that obviously the initial pressure obviously is same, because then only this mercury will remain in its position and the volume will be same. And finally, when we have changed the temperature, the mercury will shift towards one of the side, and let us suppose that this side has a temperature of 127 degrees Celsius, which is 273 plus 127, that is 400 kelvins, and this side is now at 273 Kelvin, 0 degrees Celsius. So length of the higher temperature side will increase, and let us suppose that new length is x and this length will be 80 minus x, because the sum of these two lengths will be 40, because length of mercury will not change and it will remain equal to 20 centimeter. Now we can see that pressure will still remain same, because again this system is in equilibrium. If you are considering that this pressure is higher than this pressure, then this mercury will keep on shifting towards this side. So if in equilibrium position, obviously pressure on the both sides of the gas will be same, and this will be a isobaric process. So we can say that if the initial volume of this gas is V1 and the initial final volume of the same gas is V2, then in isobaric process we can say that V1 by T1 will be equal to V2 by T2, and V1 is 40 into area of cross section, and temperature initially was 300, and V2 is x into area of cross section, and final temperature is 400 of this side Kelvin. So x will be equal to 400 into 4 by 3. So x will be equal to 1600 by 3. Okay, you can in fact 40 into 4 by 3, which is 160 by 3. So this will be the value of x, and the length L2 of the other side will be 80 minus x, and 80 minus x will be equal to 80 minus 160 by 3, and it would be equal to 80 by 3. Okay, so this is the question which is based on that type, and now we move on the next question. In this question you can see that there is a mercury column and air column below the mercury column. The length of the air column is 50 centimeter and length of the mercury column is 12 centimeter. Atmospheric pressure is obviously P naught, which is 76 centimeter of Hg. And what we have done, we have tilted this tube by an angle of 60 degree with the vertical, and we have to find out the new length of this air column. So we know that by tilting this tube, the pressure will change on the air, and therefore air will expand or contract, and let us see that what will happen. But initially we know that the pressure of air initially is P naught plus 12 rho g, and P naught is itself 76 rho g, so this is 76 plus 12, so it would be 88 rho g, the initial pressure of air, and initial volume is 50 into area of cross section. Now when we have tilted this tube, then the pressure here will still remain P naught, but pressure at this point will be P2, and P2 will be equal to P naught plus. Now we always know that the length which we have to use while writing h rho g is this vertical length. So if the length of hg is 12, so we have to take 12 sine 30. If this length is 12, then we have to consider this length, which is 12 sine 30, which is equal to 6. So it would be 6 rho g. So the new pressure P2 will be equal to 76 plus 6, which is 82 rho g. And we can say that the new volume V2 will be equal to x into area. And considering that it is a isothermal process, so we can write down, and it is also given in the question that it is a isothermal process, so we can write down P1 V1 will be equal to P2 V2. So 88 rho g into 50A will be equal to P2, which is 82 rho g into XA, cancelling A into rho g. So x will be equal to 88 by 82 into 50, and we have to compare it with this one. So it is x by 41, so this is 2, so this x will be equal to 44 into 50, and x will be equal to 220. In fact, it would be equal to 2200. Yeah. So this was the complete problems of this type 2, and you can also find these problems in many other books, but you have to remember the fact that in such problems the compression or expansion of air column is always isothermal. But if it is not mentioned in the question, then you can consider it isothermal. But if you are considering the isothermal process, then you should always check the facts that whether it will be isothermal or not. Likewise, we have attempted the previous questions in which there was U tube, and in those questions that process was not isothermal, so we used the fact that P1 V1 by T1 will be equal to P2 V2 by T2. So in moreover questions, most of the questions, it would be mentioned that it is isothermal process, so you need not to worry about that. Thank you.